All right, so yeah, I will try to present this second main theorem. So take an Abelian variety. D divisor, reduced and effective. And Zariski-Lenz entire curve inside A. So Yamanoi has this version of the second main theorem. So for any epsilon, you have the following inequality between the characteristic function of D and outside some exceptional subset depending on the epsilon, you have an upper bound given by the truncated characteristic, truncated counting function of f with respect to D, plus something which is very small compared to the characteristic function of L with respect to an ample line bundle. Okay, so it's a sort of a weaker version of the what would be an expected version of the second main theorem, since you see here you have this epsilon and the exceptional subset depends on epsilon. So it's not a small O for any, it's not uniform in epsilon. Okay, so I will try to give you some idea for the. So first of all, there are some reduction steps. So the first reduction step, is to assume that D is irreducible. Because if I write D as a union of its irreducible component, then the main theorem of the article implies that the counting function of the intersections by the main theorem, since the intersections, say, di inter dj has codimension 2 in A, then the counting function of the I inter dj for any ij difference is small. Smaller than that. For any epsilon, it is, you have an upper bound outside some exceptional subset. So this is small. So I won't write it, but if you prove the theorem for any di and you sum everything, then the difference between the sum of the counting function for any di will be equal to the counting function, truncated counting function for the sum of the di, plus something which is close to that and which is small. So you can assume, without loss of generality, you can assume that D is actually just one component. Right? D is reducible. Okay, second reduction step, is to assume that the stabilizer of this component is trivial. So more precisely, the connected component of this stabilizer, which is an Abelian subvariety of A, we can assume that it is trivial. Because if it is not, you can just prove the theorem for A replaced with A quotiented by this stabilizer and B as well. And it is not too hard to show that if you have the inequality for these two quotients, then you can deduce the inequality for the starting variant. Okay. So now let's go on to the main point. So which will be an application to the reduction steps are over. Now we apply the second main theorem, Noguchi, Winkelmann, Yamanoy. So which tells us that for some k, we have actually an inequality like that. This time without reference to any epsilon, but instead of the truncated function of order 1, we have the truncated function at order k for some fixed k. Okay, and the goal is to pass from this truncation at order k to a truncation at order 1. Right? So I will denote, I will use the same notation as Yamanoy, as d to the power 1, like that, to be the image of the jets, the one jets of d inside the tangent space of A, actually. So this typically has codimension 2. In D1A. So it's given by, if you have a local equation for D, which is, say, F, this is given by, sorry, is it really 2? No, it was 1 rather. No, 2. FDF equal to 0, apply to a point and a vector inside G, 1A. Okay, and then what you can show quite easily, actually, is that this truncated function at order k with respect to D, it's smaller than the truncation at order 1, which is the term that we ultimately want, plus something which is related to the counting function of the lift of F to order 1 with D1. And here you have a k minus 1. Okay, so the idea is simple, is that if F touches D at order k, then F will, of course, touch F at least once. So you will have 1 here. And its lift will touch the lift of D1 at least k minus 1 times at that point. Yeah. Okay, so now what we need to show, we want to show that this Fn1 here is very small, so it's something that is smaller for any epsilon than the characteristic function of F with respect to L outside some exception subset. And to do that, we will simply first decompose D1. So So if you recall, I introduced the notation W1 of F to denote the Zariski closure of the first lift of F. W1 of F is the image of F1 once you take the Zariski closure inside G1 of A. So take this intersection and write it as the union of irreducible components. And so what you just have to do is to show the inequality for any one of these irreducible components, and then you will be done. So there are two cases to distinguish. So we want to show that the counting function of F1 with respect, say, to the I truncated at order 1 is small. In that sense, I want to rewrite that every time. So two cases to distinguish. Hey. So the first case, sorry, I forgot maybe to introduce a bit of notation before that. So let me do that here. So I have this W1F, and where is it? Here. So, and as always, the idea that appears very often in Yamano's papers, so is to consider it's the stabilizer of such a variety, or more precisely the connected component at the origin of this stabilizer. So let me call it B, and let me call V1 of F the quotient. So typically, you should imagine it will be more apparent in what I will explain after that. But typically, you should imagine this V1 of F as say a vibration in jet spaces above a complement abelian variety to B inside A. So V1 of F fibers above C, which is P over B. Okay, and so the two cases will be depending on whether this Zi I'm talking about here is onto the natural projection of this W1 towards V1 of F. So that is the first thing we will discuss. Yes, exactly. It's the stabilizer inside A. So A acts on the jet space, and you look at the stabilizer in the So yeah. So now the question is, if your quotient by B, is this map surjective or not? So let me tell that here we will conclude by applying some sort of tautological inequality to V1 of F. Sorry. Maybe let me change that. But this will be in the case where this map is not onto, sorry. So here we will be able to conclude very easily by showing that, maybe I can say that orally first, and then I will get back to it in a minute. So if this map is not onto, the idea will be simply that you take an ample divisor on that variety, cutting out Zi, and then this variety has the property that the characteristic function with respect to any ample divisor on it is very small compared to the variation in B. And so in that case, the counting function of f with respect to zi will be very small. So I will do that in a minute. And the second case, if this map is onto, sorry, that's not what I explained before. And so that case is a little bit more involved, and the conclusion of some lemmas that I will explain is that in that case, we can show that the codimension of zi inside W1F is larger than 2, and then we conclude by the main theorem of the article. Okay, so two cases, one quite easy, and the other one not so much. Does the strategy sound clear? So in the first case, we will simply apply a lemma, which is very close to what Erwan explained in his first talk, actually. So the lemma is as follows. So maybe call it proposition. So this proposition is what we will use here, but let me bring the setting to you. So take a Zariski-Dense entire curve inside A. I reintroduce a bit of notation. So B, as before, is the stabilizer inside A of this W1 of F. And then the claim if I take an ample line bundle on the quotient, B1 of F as before, then we have some sort of tautological inequality saying that if I compute the characteristic function of the lift of F1 with respect to the pullback of M to W1F, I don't write the pullback, simplify, then this is very small compared to the variation of F, say, inside the variety A. So with respect to an ample line bundle on A. Okay, so what you have to imagine is that in this situation, much of the variation of F, most of the variation of F is in the direction which stabilizes this Zariski closure, and the other variation is very small. And this is crucial, actually. This is what will also be used in this second step. So since I am going to write a lot of characteristic functions, I will use a notation which will be a little bit simplifying, I hope. So in the following, when I write, so if, say, A is a variety which appears in whatever context, well, related to that one, I will sometimes write Tm of R to denote the characteristic function of F with respect to an ample line bundle on this variety. And maybe I shouldn't write F, but G. G being an entire curve going to M, lifted in whatever way, lifted, projected. So I will just write the name of the variety. So here I could have written on the left-hand side, T V1F of R is much smaller than PA of R. Okay, I will do that quite often now to avoid introducing lots and lots of ample line bundles. Okay, so the idea of the proof. is actually to climb the tower of jet spaces until we reach a point where the stabilizer, stabilize. Right? So consider the decreasing sequence of stabilizers. So now you have seen that argument quite often. And assume that it stabilizes at stage K. And call, pk is a bad choice, maybe B prime. This stabilizer once it gets constant inside K. Now I'm going to make use of the Poincaré reducibility theorem to assume that all the variety A splits as the product of all the relevant subvarieties, Abelian subvarieties. So using Poincaré reducibility theorem, so we can take an isogeny on A. It will not change this inequality above, and we can assume that A is actually equal. So you see that B prime is actually an Abelian subvariety of B since it appears after in the sequence of stabilizers. So you can assume that B itself is a product of this subvariety B prime and other subvariety C prime and C being a complement of B inside. Okay, so assume you have that. And then what happens is that WKF, so which has stabilizer B prime. So in this assumption, it decomposes as B prime times VKF. And it also admits a surjective map towards W1 of F, which is B times V1 of F. And now I'm just going to write that the characteristic function of V1 okay, maybe I should say that before. So in Erwan's talk, Erwan did that throwing thing. He proved that once you have a stabilization, then this VKF admits a finite map towards the vertical fiber of the jet space. Maybe I will write that here. Then VKF towards, say, JKA, this natural projection map is finite. So if you take, say, a completion of that, maybe I can take a completion. Oh, not finite, but generically finite, rather. Sorry, generically finite. So it implies that if I consider the characteristic function on the left-hand side, so I can do it with respect to any, say, ample or big line bundle on this variety. And since this map is generically finite, if I take an ample line bundle here, once you put it back, it will become a big line bundle. And so you can use it to compute this function. And writing that you compute this function with respect to a pullback of an ample line bundle here, you get an inequality like that, maybe with a constant. So the characteristic function of f on this variety, the variation in this direction is smaller than the variation in the vertical fiber of the kth jet space. But now you have the tautological inequality telling you that this is very small compared to the variation of f on the Abelian variety. Thanks. Okay, so maybe let me repeat the argument. Once you have this stabilization, you have this projection which is numerically finite, and now you can pull back an ample line bundle here to get a big line bundle here. This characteristic function with respect to this big line bundle will be larger than any characteristic function with respect to an ample line bundle. So you are allowed to write this. And this by the tautology inequality is very small. Okay, and so what we just want to do is to compare the TV1 of f bar, if you want, with this one. And so that is very easy, actually, because we have a dominant map. So say this is smaller than the T of this product, C prime times V1 F. But here, actually, if you just focus on this fiber, you have a surjective map like that. So it is smaller than the characteristic function with respect to the variation at order k in the vertical fiber. And then you get something which is very small. Okay, so, and I did it for order one, but it works at any order, actually. To replace one, you can put an I here. It will work all the same. Okay, and now we can conclude in the first case, because maybe I can write that here. If the map from Zi, which I repeat, lives inside this J1 of A, for which, so we want to show that the counting function of this Zi is very small. And if this map is not onto, if it lives if it falls inside some algebraic subset, so you can just let, say, E in J in this V1 of F bar, say, be a very ample divisor with support containing the image of this Ci. And then what happens is that if you take the counting function of Zi for the only lift that makes sense, then it will be smaller than the counting function with respect to E for, again, the only lift of F that makes sense, so inside V1 of F. But E also then is very ample on this variety. So here you can use the first main theorem, telling you that you are actually have something which is smaller than the characteristic function for a given ample line bundle on this variety. But here we have said that this is very small. The characteristic function on A. Okay, so this is actually the very easy case. But now let's go on to case 2. So here, I must admit that I have not delved too much in the details of Yamano's proof. So I will try to explain you an argument which I believe is basically the same, which might not be fully complete, but yeah, if it's not, I certainly hope that we can fill in the gaps. Okay, so we will need first some lemma. So the idea, maybe I should say that first. The idea will be to use a fibration of this Zi over another variety and basically count the dimension of the generic fiber and show that it has to be at least 2, well, the ambient variety minus 2 at most. And for that, we will need some lemmas allowing to count dimensions. So again, let me introduce. B will have the same meaning as before. Let me call phi the map going from A to the quotient A over B, which I will denote by C as above. Now, let me do the same thing for the map phi composed with F. So B prime will be the stabilizer inside C of the W1 phi composed with F. So I have a new Abelian variety and I do exactly the same as before, but this time with the map going from C to C. And let me call phi prime the map, well, this time going from C to the quotient C phi B prime, which I will call C prime. Okay, and the claim is that the dimension of, well, the first quotient, yes, W1 of F by B is strictly larger than the dimension of this W1 of this composition. So you drop dimension, well, on the left-hand side, you still take the quotient. So let me just say how it will be used. The argument in the proof, actually. So this map is on 2, it's not hard to see. And the claim is just actually that this map is not generically finite. It has positive dimensional generic fibers. Okay, so here, as I said, the argument in Yamano's paper is quite involved, and I think maybe we can simplify a bit the idea. So proof, question mark. So again, assume that we have split everything by Poincaré reducibility theorem. It will not change any of the dimension counts we are doing. So assume that B, maybe here I changed the notation B prime, C prime compared to what I did. So be careful here. B prime times C prime is the C. Okay, and now we also have this W1 of F, which I can write as B times some vertical fiber, V1 of F. And similarly, W1 of F rho phi rho F, a circular F, is B prime times some vertical fibers. Okay, so assume by contradiction that this map is generically finite. So by contradiction, if that is the case, so what you can do is to write a diagram. So on the left-hand side, okay, what do we want to say? Yeah. You will have this W1F, I will send it to B prime times V1 phi rho F. So what I'm assuming actually is that this map is generically finite. And on the bottom side, you can project everything down to A, and similarly on the right-hand side, you project the things to B prime, then C prime. And now I'm going to write a sequence of inequalities that will turn out to be impossible to satisfy. It will be the usual thing. I'm going to write that the characteristic function is a small o of itself. Using the tautological inequality. So first of all, oh, okay, so maybe. Okay, so what I wrote, and I realized, well, so there was a question mark. So what I wanted to write actually is that you can write a sequence of inequalities starting from that one and arriving at the end to this. So again, I write a TB of R to denote the characteristic function of F with respect to an ample line bundle. But here I realized that what I wanted to write, I swear, it seems that I used instead that this map is generically finite, which is not what we want to contradict. So what I wrote is this. This is wrong, I think. I hope it's able to correct that. Well, the conclusion of the lemma is true, but my proof is I think there is a mistake. So what I wrote is that we have this inequality simply because we can add an ample line bundle on that part. And now I said that since, this is not true, but I wrote that the idea is that if this map were generically finite, then you could pull back a very ample line bundle on that part to the left-hand side and use it as a big line bundle for which you can compute the characteristic function. So I wrote this. I think it's not true. Yes. I want to show that this map quotient by B. So there shouldn't be a B here actually. So you see, I need to bound from above TF of B, and I thought it was. Yeah, it's quite weird how I didn't see that. But now, once you have that, if it's you just use the proposition I told you before that. If I consider the map phi rho rho F, then the characteristic function in the vertical direction is much smaller than the characteristic function in the direction of the stabilizer B prime. So now this becomes a big O of TB prime R. But B prime now lies in the direction of V1 of F, and so itself, it's smaller than TV1 of F, which by the lemma is much smaller than TB of R. So here, the problem is there. So in Yamanoi's paper, he uses, well, the second main theorem, again, by Noguchi, Winkelmann, Yamanoi. I thought that we could bypass that by a simple argument, but apparently it's not the case. Well, I don't know. Yeah, I don't know how you can bound TBF from above like that, actually. But okay, maybe I will think about that and I'll tell you if I find. Okay, so let's assume that we have a proof that this map is not jointly finite. Now what we are going to consider. So, yeah. Okay, so we consider the projection of G1 of A towards this quotient G1 of A over B, which is actually none other than C times the vertical jet space, first the jet space at A for A, so with the notation of before. Now, in the quotient, consider the following locus. So it will be the locus of points in C and vertical jets, such that the codimension of the intersection of the fiber above that point with D1 is actually not the expected one. So here I recall that this has codimension 2. So consider the locus where you have excess intersection. And what I claim is that once we have the following lemma, which says that if you consider the image of W1F inside that variety, so means that you simply quotient it by B, well, it doesn't fall inside this excess intersection locus. Which means I have erased that, but this will imply okay, so this will imply that if you recall, I had this map of Zi towards, so what was it? V1 of F. So in the case where this map is dominant, you can simply do the exercise. If this map doesn't fall inside the locus where you have excess intersection with D1, then the codimension of Zi, which is just Zi, is just a component of the intersection with the D1 here. So this codimension inside the W1F will be larger than 2. And then we will be able to conclude using Yamano's main theorem of the article. Okay, and well, I will take that on the board. And so the idea to obtain that result is to, well, reason by contradiction, assume that you have excess intersection with D1 everywhere. By contradiction, assume that W1 of F, quotiented by B, falls inside this intersection, excess intersection locus. So it means that, so if you recall, if you want to cut out D1 with such a fiber, you need two equations. You need locally F and D. So if you have codimension lower than 1, it means that the equation dF doesn't bring any new information compared to F. So basically, it means that for any C and psi inside of, say, dA, so C times G1 of A, if psi is tangential to some point of the fiber DC. So DC is just, you have that. Let me assume that the variety A is B times C, as before. So I have this, I can choose a point C inside the vertical fiber, and DC is just the intersection of the slice of vertical coordinate C with D. So the assumption is that if you have excess intersection at the point C, it means that if you have a vertical jet which is tangential to DC at some point, then it is actually tangential everywhere. It's say point Y, then psi is tangential to this DC. So here it's important to note that I'm talking about the tangent space to DC inside A. So I'm saying that if I have a vector like that, going in any direction in the Hermitian variety, at some point of the slice DC, then I can move that vector anywhere along the slice DC and it will remain tangential. And now you see that I will derive a contradiction by producing such a vector, which is actually tangent to the slice itself. So basically going in the direction of B. And then I will get a tangential vector field to DC at any point of DC, then giving you a one parameter subgroup which will stabilize DC. And that will be the contradiction with the fact that we assume that D doesn't have a non-trivial stabilizer. So since I'm going to explain that, and then I will explain how you can obtain a tangential vector lying inside B. So since the stabilizer to D is trivial, then there is an argument which is quite similar to the one Damian explained to us, but maybe a little bit simpler. So if you have a global stabilizer like that, then for C generic, inside the C, lying in C, in the image of D, then the stabilizer of DC, which is a subgroup of B, is also trivial. And so the idea now is to take C, a small C generic, and to show that we can find a psi which lies in the tangential direction to B instead of A, and get a one parameter subgroup inside B, stabilizing this DC, and then giving a contradiction. And so why can we find such a B, tangential vector lying inside B? Well, it comes from the lemma from before. So by the previous lemma, so this map W1 of F going to actually the first set space of C has actually generic positive dimensional fibers. That's positive dimensional generic fibers. So this means that if you take now C inside that generic, then you will be able to find the whole the vectors inside. So this W1 of F quotiented by B, this is something which I denoted by V1 of F. And by the reduction, well, Poincare reducibility, you can write it as something which fibers above C and which gets sent also to G1 of A. Like, and so if it has positive dimensional fiber above a generic point inside this G1 of C, you will be able to find points, so C and zeta, depending on one parameter, such that their images inside G1 of C. So all this zeta of T will be sent to this psi of T. And so the difference between two of them, say, will be something which is tangential to B. And so, yeah. So now the assumption is that if you take C psi in the image of that map, so all these zeta T will be tangential to the variety DC. All the pre-images zeta T are tangential to DC. So, is so are these zeta T minus Z0, which does and are lying inside D. So by taking these pre-images, you get your one parameter subgroups, and thus you have the contradiction. Okay, so yeah, I should reread the proof of that lemma, which is you see crucial to get these positive dimensional fibers and thus these one parameter subgroups. It's more complicated than what I thought, but not surprising because the proof is quite technical. But yeah, I still believe there might be some simpler argument. Right, so maybe let me stop here. Thank you. The organization. Thank you for the organization. See.